So we've now completed our survey of Chapter 8, which is preparation of alcohols. We want to turn our attention to what other functional groups can alcohols be turned into. We saw in Chapter 8 that they can be oxidized by chromium-6 reagents to form carbonyl compounds. What else can we do with alcohols? And one of the things that we already saw, because we needed it in our synthesis, is the transformation of alcohols to alkyl halides by treatment with concentrated aqueous HCl or HBr. So we saw that ethanol can be converted by reaction with aqueous HBr into bromoethane. And you will actually carry out a reaction very similar to this in the lab, where you'll start with 1-butanol, and you'll react this with a mixture of aqueous HCl and aqueous HBr in equimolar quantities to form a mixture of chlorobutane and bromobutane. And we will be able to use the ratio of chloro and bromobutane formed to determine something about the mechanism of this reaction. Since this is a primary alcohol, and it's a substitution reaction happening at the primary carbon, you can probably guess that it's likely to be an SN2 reaction. So what's the mechanism for the reaction that converts a primary alcohol into a primary alkyl halide using concentrated aqueous acid? Water is not a good enough nucleophile to push a leaving group out in an SN2 reaction, and we can't lose hydroxide ion, right, because hydroxide ion is a terrible leaving group. What we're going to have to do is convert that hydroxide into something that can leave. Well, we know that aqueous acid is quite reactive. We know that aqueous HCl immediately dissociates to form hydronium ion and chloride ion, and aqueous HBr immediately dissociates to form hydronium ion and bromide ion. So the source of acid in this case is the hydronium ion, which is the strongest acid that can actually exist in water. Any acid that's stronger than hydronium ion is immediately going to protonate water to form hydronium ion. This equilibrium constant will be very similar to 1 because the protonated alkyl oxonium ion is expected to have a pKa very similar to hydronium ion. There's really not that much difference with an R group associated here versus another hydrogen. We have chloride ion and bromide ion in solution. The next step will be to do an SN2 reaction to kick out water, which as a neutral leaving group is a favorable reaction. In order to show this mechanism properly, I need to actually have the reactive carbon written out. I need my leaving group water and my nucleophile chloride to be in the plane of the board, and I can show the backside attack of the chloride ion. Because this is a concerted reaction, customary to show the transition state where we have the carbon-chlorine bond forming at the same time as we have the carbon-oxygen bond breaking. We have a partial positive on the oxygen and a partial negative on the chlorine. And we have gone to a trigonal bipyramidal geometry on carbon. And when we're done, we will have inverted the stereocenter. Though since it's not a chiral center, you won't notice that you've inverted. So it's pretty simple. Step one is just a protonation. To convert the unfavorable leaving group hydroxide, which won't leave in nucleophilic alkyl substitution, to a favorable leaving group water. And then step two is an SN2 substitution. It's the inverse reaction that we did before, where you took an alkyl halide and reacted with sodium hydroxide in a polar aprotic solvent to do an SN2 substitution reaction to convert it to a primary alcohol. Works the same way with HCl and HBr. The acid source is the same. It's hydronium ion because that's what both HCl and HBr will be converted to when dissolved in water. The same reaction can convert tertiary alcohols into tertiary alkyl halides, but because the substitution reaction now happens at a tertiary carbon, the mechanism will switch from being SN2 to being SN1. So, for example, we can take tertiary butanol, or 2-methyl-2-propanol, and treat it with aqueous HBr, which we know really means hydronium ion, bromine ion, and the mechanism will be similar. A reversible proton transfer to convert the OH group, which can't leave, into a fine leaving group, water, neutral water, it's a great leaving group. But now, since it's a tertiary center, it can leave spontaneously. To form the tertiary butyl carbocation, water, and the tertiary butyl carbocation is now attacked by bromide ion. To form tertiary butyl bromide. It's a three-step reaction: protonation, loss of the leaving group, and attack by the nucleophile. So one additional step, because the substitution pathway here is SN1 at the tertiary center instead of SN2 as it was for N-butanol or 1-butanol. You'll notice that this reaction is the exact reverse of the reaction of a tertiary alkyl bromide with water in the Sohola-6 reaction. Exactly the reverse. It goes through exactly the same intermediates. The reverse reaction would have been loss of bromide to form the tertiary carbocation, and then a proton transfer reaction to generate the neutral alcohol. The principle of microscopic reversibility says that if you have an equilibrium process like this, it has to go through exactly the same intermediates in the reverse reaction as it does in the forward reaction. If we want to make the bromide from the alcohol, we need to use a relatively concentrated solution of HBr so that we keep the concentration of water as low as possible while maximizing the concentration of bromide. If we want the reaction to go in the opposite direction from the bromide to the alcohol, we want to use a low concentration of bromide. We'll add no additional acid and a high concentration of water, right? So water will be the solvent in that case. So it needs to be concentrated HBr, and concentrated HBr is about 48% by mass of hydrogen bromide dissolved in water. If you wanted to make the corresponding alkyl chloride, it would need to be concentrated HCl, and concentrated HCl is approximately 37% HCl by mass dissolved in water, which is about 12 molar HCl. You need to keep the concentration of water low to go in this direction, and the concentration of water high to go in the other direction. So this is great. We can make primary alkyl halides from primary alcohols, and we can make tertiary alkyl halides from tertiary alcohols. Can we make secondary alkyl halides from secondary alcohols? Well, the answer is yes, sometimes. It depends on the structure of the secondary alcohol. If we take 3-methyl-2-butanol, and we treat this with concentrated aqueous HCl, which we know is 37% by mass, or 12 molar, we would expect to get 2-chloro-3-methylbutane if it underwent a simple substitution reaction. As it turns out, what we really get is 2-chloro-2-methyl butane. We don't get a secondary alkyl chloride, we get a tertiary alkyl chloride. Something goes wrong along the synthetic pathway that causes a rearrangement. That's a complication that doesn't always arise, but it arises often enough to become a problem. If we were to simply take 2-butanol and react 2-butanol with aqueous HCl concentrated, we could expect to get a reasonable yield of 2-chlorobutane by the same mechanism that we just saw for creation of tertiary butyl chloride from tertiary butanol. But if we have a beta branch, we don't get the expected product. We don't get the chloride in the same position that the alcohol left from